All right. So then S of t is the time series of a dipole, right? Because and we were kind of postponing this thing, right? We looked at it, right? I wrote to you this couple of formula how to do it, like, and but didn't pay much attention to it on purpose because the main goal here was to actually find these two guys, okay? And of course, we consider the case when we have multiple dipoles, so it was R1, theta 1, right? R2, theta 2. And usually we've played with MATLAB, we've played with only two sources. We could have added the third source, but the point is that there are few sources we were playing with, but the key point was that we were not aware, we didn't know where these sources in the brain are. And our task was to find the parameters of these sources to localize the sources, right? And finding the parameters, the sources was basically our main goal. And that's why these methods that we have considered so far as to just simple scanning, dipole scanning, then music method, rap music method, they were all basically, they are all called so parametric methods, okay? Parametric because they are finding the main goal of ours is to find the parameters of our sources, okay? These are the parameters of the sources, okay? And the time series itself is not really a parameter. Okay, of course, it's all in terms of like how you define it, right? But we assume it's not a parameter, okay? It's a property or whatever, but it's not a parameter of this activity. There is another family of methods that is called non-parametric methods, okay? And in those methods, what we do, we take the brain and we say that our dipoles are located everywhere, not of course everywhere. You have this mesh, right? Triangular mesh, triangulated mesh, and each location of this mesh, you assume that there is a dipole, right? There's a dipole, and your goal, and with this, you basically say that you know the parameters of your dipoles, right? Because you know the location of each dipole, right? And for each dipole, you can compute for each location and orientation, you can compute the forward model, of course. And then you say that, okay, but now my goal is to estimate the time series of the sources, okay? And by measuring the power of these time series in each location in the brain, you can judge about the presence or absence of a source at that location, okay? This is a different, how to say, how to say it, completely different approach, right? It's completely, on the one hand, on the one side, hold on, why? Again. Yeah.
What do you mean by saying a power of time series? Is it duration of time?
I mean, yes, I mean, just a second. Again, Samsung Galaxy is giving me hard time. Now, yeah, okay, now I got it. Okay, so just a second, please, bear with me. This is horrible. I mean, let me quit the conference now. I'll explain everything. Just a second. Doing something.
Okay.
Sorry. Okay, let's quit Zoom. Let's quit this. Let's quit this. Let's go back to the Zoom. All right. Yes, my name is Alex. This is very good. Понятно. Okay. Поделиться. Screen. Начать. Okay. All right. Yeah. Now it's back. So, but your question was, what do you mean when I say that we are trying to find the time series, right? We are trying to find the.
You said power of.
The power, yes, the power of time series. I mean that, for instance, if you have time series, something like this, right? And then for some other source, you have time series, something like this, okay? And then for some yet another source, you have time series, I don't know, something like this, okay? something like this. Okay, and then that means that basically you have a you can measure the power, so you can sum the squares of this time series for each time slice. Okay, you can sum s sub I of t squared over this interval. Okay, and based on this you can judge about the presence of the of a source, or alternatively you can just simply select a latency in time, right? You can say that, okay, let me select this latency and then look at the amplitudes, or at amplitude of your sources, and then you can say, yes, this source is present, this source is present, but the third source, the red source, isn't there, just because the power is very low. Okay, so that's what I mean. Okay, so the task is basically, you know what, there is something. I know what happened, and but I don't know how to resolve this. I know what happened. I disabled all smart gestures, and it turned out that this is a smart gesture. This is a super smart gesture. Okay, let me then try to somehow. And interestingly, it works sometimes, but sometimes it doesn't. Yeah. This is interesting. Okay, so I broke the rule of a software developer, of users of the software. Never change anything that is working, even if it's working not very well. When you change it, it will work worse. It's horrible. It doesn't listen. That doesn't obey me at all. Hmm. No. No. Hmm. And what should we do? Let me try this. Okay, now. Okay, that's the first step. This is good. Okay. I can't bring up the controls of the problem is that I don't have I have my old pad, but in this computer I don't have a way to connect it, and therefore I have to use this piece of crap. Hold on. Yeah, I'm sorry, let me reboot this thing. I don't see any other way. I will remove this, and then I will enable all super smart gestures, and maybe after this will be working. So yeah, let me continue talking before we so that okay. So and then when we were so basically we are changing the problem from finding the locations of sources, right, and parameters of the sources, to estimating their magnitudes. Okay, so basically you have on the one hand, on the one side you have the time series of your sensors, right? On the other hand, you have your brain and you have your sources. This is sensor space. This is sensor space. This is source space. Okay, and between these two, you have forward model matrix. Okay, and your goal in this other class of method that we haven't considered yet is to basically somehow use the information about how these sources map onto the sensors and invert it and infer the time series of your sources from the time series of your data. Okay, so let me, hold on, it rebooted. Now let me try to okay, now it has to be in advanced, двойное касание, при выключении экрана, двойное касание для включения экрана, не выключать при просмотре. I don't even know, this is like движение, жесты, быстро collapse. I disabled everything, but now I don't know what I disabled. Okay, so положение. Вырос полностью. I don't know, but well, I don't have any good expectation about this, but let's try. Let me see. So see, without Zoom, it's working perfectly. And I have also made another mistake. I updated Zoom. So there are two mistakes at the same time. This is like I must have been fired already, for this. So wait, let me see. Let me see. I'm sorry. I'm wasting your time, but yeah. Okay, now this one. Okay, this one is working now. Now we need to go to Telegram and Telegram. Here is the link. Let's see. Okay. All right, so let me first stop video because it's an unnecessary distraction. Screen, значит. Okay. Okay, so far it's working. Let's make more pages. Okay. Yeah. All right. So let's continue with the prayer. Okay. So so yeah. But today we will be so basically is I what I just stated. So here is your sources. Here is your data, right? Uh, and this is your forward matrix, right? And so you're observing this guy and you want to infer this guy, right? So because in the dipole fitting scenario, we were finding a couple of sources or like three sources, whatever, and then we were saying, okay, my x of t, my data, are equal g1, g2, g3, for instance, right? Multiplied by S1, S2, S3 of T, right? And you were assuming that there's some noise, okay, whatever. And then you were asking, okay, now once I have found my locations, remember those peaks in the rap music scan, right? So we found these peaks. So basically, and we populated the so-called the matrix of independent topographies, this matrix G, right? Where in this case it's very small, right? It's number of sensors by 3, right? So it's a tall matrix, right? So it has 3 columns and quite a bit of rows, right? And then you were asking, okay, so what am I S of T, right? And then the trick was I was teaching you with this without like much of understanding, but just a trick. So because this matrix, you can't really compute inverse of this matrix because it's not square, right? Because it was square matrix, then of course you just compute g minus first x is equal g minus first times g times s, and then this becomes identity, and there it's equal s, right? But in this case, in the case when g is not square, you can't do that, and therefore I was showing you this trick. You just simply multiply by g transpose on the left, g transpose g times s, and then this one is already 3 by 3 matrix, right? Because it's g is tall. When you put it on the side, it's 3, and then multiplied by itself. Then you can take this guy minus first multiplied by g transpose x will give you sources. Okay, so and this is what's called pseudo inverse. Well, almost. Okay, pseudo inverse of well, yeah, you can think that this is a pseudo inverse of g. Okay, and it's very simple to show because it's minus first times g, right? G transpose. And if this is a pseudo inverse, a left pseudo inverse, then when the matrix multiplied from the left, it should give you the identity matrix, right? Then you multiply it by this g from you multiply this by this g from the left, and you clearly see that this guy is exactly inverse of this guy, or this guy is exactly inverse of this guy, and then this is equal identity. And that means that you, in the case your model is G times S, right? Then once you have multiplied your X on the right, on the left hand side by this matrix, which we will call W, right? It's called G transpose G minus first G transpose times X. I will substitute this X, right? You will have G times S. You will so here, right? So you will basically get your time series S. Okay. So this is, we have already done. The key here is that matrix G, I will repeat again because it's very important, is a small matrix. Okay, let's say three columns, right? Maybe four, but usually, right? And therefore this trick works, okay? Because G transpose G is, in this case, is 3 by 3. G transpose G is a 3 by 3 matrix, and it's full rank, most likely, you know, because if topographies are not collinear somehow, you know, the sources are, of course, if the sources are super close to each other, then it won't work. But if they're at some reasonable distance, then you will have no problems of recovering the three dipoles, the time series of each of these three dipoles, and you can judge about their relative strengths, right? But today we will consider the situation that is in between the full-blown inverse when we have sources in all locations in the brain, and the situation when we have 2 or 3 sources. Okay, and then we will consider this was dipole fitting. Okay, dipole fitting. This one is so-called, yeah, and this is parametric method. Okay, parametric. And this one is imaging method, okay, where our source model is a distributed source, okay, distributed across entire cortex, right? And this is what you call, I don't know, it's actually called non-parametric. Let's put it this way. Let's put this one as imaging, okay, and we put non-parametric here, okay. Non-parametric, okay, because we are not finding. We will look at something different here, which is somewhere in between, and it's called beamforming. Okay, beamforming. Okay, it's a very popular method that became popular like maybe 20 or something years ago, and people that been spending quite a bit of time in this source estimation and EEG and MEG. They were actually kind of, you know, they were not very sure that this thing would work, because they all got used to either this dipole fits or these non-parametric imaging methods, where in both of these methods, in this one and in this one, both of them are global methods. Okay, so basically what this means that you are trying, remember when we were plotting this time series and we were finding dipoles and we were projecting the dipoles time series on the sensors and then subtracting one from another and looking at for the error, right? What is the error, right? So they are global in a sense that if you have your X of T data, right? Let's say you have your X of T data in multiple channels, whatever, something like this, right? And then you have your S of T, right? Let's say like 3 sources, for instance, one source, another source, and the third source, right? Then if you apply your forward model to this, you get something which hopefully resembles very well your observed data, and your error is as small as possible. So this is error, okay? So it's a global method in a sense that both of them are global methods because they are trying to explain the data completely, okay? Well, completely, not completely, depends, right? Depends on the noise model, but they're trying to explain the data. So you say that, okay, what is the explanation? What is the configuration of dipoles, and what is the time? What is the set of what is the time series of these dipoles that explain my observed data? And there it is. Or what is the distribution of the activity on the cortex? Okay, like patch here and patch here. such that this activity explains my data that I observe in the sensors, right? So your leading star, your functional, your goal was to actually find such a underlying distribution of sources, either by specifying, their intensities simply, or by finding their locations and then finding the intensities, in order to explain the observed data. Okay, beamforming doesn't care about it. Okay, beamforming doesn't care about explaining the data globally at all. Okay, what it does, it simply gives you a recipe how you can listen to a particular source at a particular location. So beamforming came into this field from radar theory, from this electromagnetic or acoustic radars, which is basically a tool to listen to a particular direction, right? So in the simplest case, like you have, if it's an electromagnetic radar, right? What you do, you have an antenna, right? You have an antenna, and this antenna has certain beam response. Okay, it's certain direction where it's sensitive to, and if you have an object here, then this antenna will be sensitive to this object, but it will not be sensitive to this object. Will be less sensitive to this object because, let's say, angle for this object, and it will be even less sensitive to this object because this is the intensity with which it is sensitive to this guy, this is the intensity which is sensitive to this guy, and this is maximum intensity at it is tuned to this location. Okay, and it's basically staying there and listening, or it can be scanning. Okay, it can rotate this guy, right? It can rotate this guy, it can point in this direction, this direction, this direction, this direction, this direction. It can be scanning beamformer, right? Or something, it's another way, right? It's scanning and finding sources every time it is sensitive to a particular narrow location. Okay, and the narrower it is, the better. Okay, so that's exactly how it's used in our business. Okay, in EEG and MEG model, and here, by scanning and measuring the intensity, you can make judgment about whether sources were present, right? Because if you draw your scanning diagram, where this is the angle, this is physical space, okay, this is just normal angles and everything, right? And if your scan looks like this, something, nothing, but then there is something, and then maybe there's something, yeah, then you know that at this direction you probably had a source, right? Because you have high amplitude at this angle and low amplitude to other angles, right? So very similarly, we will use beamformers when we want to understand and actually create a picture of where the sources are, okay? But the primary goal of the beamformer is not this. The primary goal of the beamformer is to listen to a source at a particular location, okay? And we will develop this methodology for this today, okay? So another example, maybe simpler for you to comprehend, acoustic radar, okay? Like our ears, basically, okay? We have two mechanisms, okay, with which we determine the direction to the object, to the sound, okay, which is producing a sound, okay? The first mechanism is simply based on the phase difference, okay? So when you have a source here, you have if it's far away, then you can say that your acoustic front is flat. Then okay, then at this sensor, the signal has come earlier, and at this sensor, the signal has come later, and this is delta t, right? And this delta t tells you about the direction at the source, right? On the one hand, right? On the other hand, you can tune your processing to be sensitive selectively to this location, because see, if you know the frequency, right? If you know the delay, right? Then you can be, or you don't even have to know frequency. Okay, if you know the delay, all you can do, you can take this signal, okay? Then you can take this signal and delay it by delta t, but this delta t is clearly the function of this angle, right? Of this angle, right? And so if you want to be sensitive to this angle, then you say that, okay, delta t of alpha, okay, this is your delay, and then you simply sum the two, okay? You sum the two, and this is your output, Okay, now how will it work? If you assume that this is the first time series from the first sensor is some harmonic this way, on the second sensor you will have a different harmonics, right? Which is the same harmonics, the same frequency, but let's say it's shifted. It's shifted by delta t, right? If the delta t is the one that corresponds to this, to the direction that the one that you should listen, then when you shift this guy with respect to this guy and you sum them up, you'll get maximum signal, right? Of course, you need to take then the absolute value of this, right? And then you get the maximum signal, right? If you don't sum them up, you will not get maximum signal. You can have another process. You can take the product of the two instead of measuring the sum. Pretty much the same thing, right? So the point is that you can tune the parameters of your processing tract, and in this case, it is only this delay in order to become sensitive to a particular direction, okay? To a source at a particular direction, okay? In electromagnetics and this problem of from your homework comes actually very handy here, because what it tells you that in the circumstances that we are in, okay, with the conductivities that we have, brain conductivity, head conductivities, and with the frequencies that we are dealing with, delta t, the difference between the signals that we measure at the electrodes is negligible, okay? If you talk about physics, okay, the signals occur simultaneously on all sensors. It doesn't mean that they all occur with identical values. No, in some places they will occur with negative, in some places with positive. Remember these topographies, right? So, but they will, the source, that when the source appeared, it will be seen immediately on all sensors, okay? Therefore, there is no such thing like the delay, okay? And therefore, the delay is not a parameter for us. But still, we have a parameter because which describes how a source is seen by the sensors, right? If we have the head, if we have a set of sensors here, right? If we have a source here, we have this forward model, right? And this forward model basically a set of coefficients, G1, G2, G3, G4, G5, right? That these are the scalars that all result in, this is the first source, for instance, a G1 vector is equal, let's call it G11, G12, G13, G14, G15, right? And this is G11, G12, G13, and etc. G1n, where n is the number of sensors. This is the vector that tells you how this source manifests itself on the sensors. Okay. So, and this is your model. Okay. Now, if you want to listen to a particular location, you may want to ask, yes, and how we will implement it, okay? So how we implement it, if we have the time series x of t multivariate time series x of t multi-channel, then we will be looking for such w, a vector, okay? So that at the output, we have activity for an estimate of the activity of the first source, for instance, okay? So it is entirely possible because, see, if your x of t is g1 s1 of t plus g2 s2 of t plus g3 s3 of t, and etc., and let's assume there are not so many active sources, okay? I mean, not like thousands, right? Then it's conceivable that you may be able, if you are in like 100-dimensional space where 100 is number of your sensors, right? So it's conceivable that you can find 100-dimensional vector w that is, when multiplied on the left by x of t, will ensure that this guy is passed with gain 1, basically with scalar 1, right? And the other guys are passed with much smaller gains, okay? Or better yet, with 0 gains. So basically, if you substitute it here, you will get wg1 s1 of t plus w g transpose g2 s2 of t plus, and etc. w2 g, I don't know, p times s of t, okay? So see, these are scalars, right? These are scalars. And all it tells you is that you're just simply your output of your beamformer, okay? Let's say Z of T, okay? The output of your beamformer is simply a linear combination, a summation of activities of different sources, but with different coefficients. If you are interested in listening to the direction in quotes here, okay, corresponding to the first source, then you may want to say that, okay, I want W transpose G1 to be equal 1. And ideally, W transpose G2 should be equal 0, W transpose G3 should be equal 0, and etc., W transpose GP equal 0. Agreed? Just, you know, because you want such a filter that isolates for you this source. So you need to emphasize this guy, and it has what, how do you say that this source is something you want? Well, this source has certain signature, and the signature is its topography, okay? And then you use this information in order to basically make your algorithm selective, okay? There is one problem. The problem is you don't know in general where these sources are. Okay, you may know which source you want to listen to. Okay, you may imperatively say that I want to listen to a source in the parietal lobe somewhere, like where my alpha rhythm is, right? I want to listen to this particular source, and you can say, okay, this is the topography I want to listen to. I don't know anything. I mean, just make me a filter that has gain 1 at this topography. Well, there is one possibility to make, basically can take any vector except that it's orthogonal to this topography and then scale it, right? You can just assume that your V, your W is just any vector V, okay? Any vector, any, except V transpose G1 should not be equal 0, okay? It shouldn't be orthogonal, right? Then in order to make gain 1, in order to make sure that W transpose G1 is equal to 1, you can scale this vector, you can scale this V as much as you want, but then it will be basically nothing special. It will not be really doing something for you. It will not be isolating the sources, right? Because again, let's say this is already abstract space, okay? This is your G1, right? This is your vector G1, okay? And this is your vector V, okay? And then in this case, V projects on G1 with this value, and you know the project and you want that this W transpose G1, which is simply the norm of this, right? Which is norm of this multiplied by the norm of this multiplied by cosine between these two angles. You want this to be 1. You can always find a scalar that will make this to be 1, right? So you take any vector V divided V times G1, and that will be your W, okay? But this is bullshit, you know. This is what I mean. That in terms of, if we talk about the direction, and we are talking basically about the direction, we're talking about selection. You mean any vector of any shape V will work as a beamformer? No. I mean, well, obviously, no. I mean, how? You need something else, right? You need some property of optimality, something which will ensure that the signals that you are getting will not have noise in them, will not have contribution of other sources. But you don't know where these other sources are. You don't know where they are. So you don't know their topographies, okay? If you knew their topographies, then yes, you can say that, well, yes, please implement this set of constraints for me, okay?
I have a question about
Yeah.
this set. I thought that the contribution of I mean, I thought that V is some coefficient or the set of coefficient matrix that changes when we multiply it by G. It changes value of G. I mean, you explained this in radio waves, how and from this logic, I thought that we
Yeah, exactly.
gives us some
Exactly.
so
V
here
yeah. Yes.
Here the here we have 1 and 0 0 zeros because the value of we have different values of w, not different values of g. Yes, because
No, see, listen. We want this constraint, okay? If we want to listen to source G1, to source located at G, who has topography G1, okay? We want to select such W, okay, such vector W that
mhm.
that makes scalar product with G1 equal 1. So it basically projects on G1, okay, and orthogonal to vectors G2, G3, GP. Okay,
Ah,
it's like
so
you just think about it in the multidimensional space. But I mean, here this is G1, this is G2, this is G3, this is whatever, and then you want to find such W that you have gain one, you have projection on this first one, and orthogonal to all other guys. Because if you are orthogonal to all other guys, you will not listen to them, and you will solve the problem.
so from what you say now, I can so we have the same values of g. They are fixed. Yes, here G1, G2, G3. They have это
They
данные.
are yes. Well, okay. I'm approaching gradually to beamformers. Okay, they are not.
Мгм.
You don't know where they are. Okay, they are doneness. Okay, they are there. Okay, you assume they're stationary. Okay, but
Ага.
you don't even have to assume they're stationary. But anyway, if you, in the end, you don't have to assume they're stationary. But you have yes, you have certain I'm just trying to approach it. I'm saying that, okay, imagine that you have, let's say, p sources, okay, and imagine
Мгм.
that they're active, okay. Now imagine that you are interested in finding a filter W, a vector W, that would filter out the activity of the source one and
Мгм.
suppress the activity of
Activity
all
of
other
others.
sources, right?
Yes.
So
Ага.
again, I will make this analogy. Like, imagine that you are you are in the crowd, okay? Imagine that you are in the crowd, okay?
Мгм.
There you are. This is your nose, these are your ears, okay? And the crowd is all around you, okay? There are people all around you, okay? And you want to listen to this guy, okay? Then you, of course, you turn yourself to so that your nose points to this guy, your ears are, tuned to his mouth, right? And this way, right? Now imagine you have enough, and this crowd is speaking, but it's very monotonically speaking. It's coming to you from all possible sides, okay? So you there is no point in actually trying to tune away by rotating yourself from the target, from the crowd, because the crowd is everywhere. Okay, so all you need to do is to tune at this particular person who is speaking, okay, to this guy. But then imagine that there is another guy came here, and he's also speaking very loudly, okay, and very annoyingly, okay. And so, but you want to listen to this guy, okay, but he is speaking directly into your right ear, okay. And you're just basically so badly confused, you can't listen to this guy anymore. And you're trying to find the location, the direction, so that you cancel this guy as much as possible while maintaining some tuning to this first guy, okay? And it's most likely, it's possible to find a location where signal from this guy will be diminished, but signal from this guy will be sort of, maybe the best solution is this, right? It's one ear here, one ear here, and you're back to
Yes.
this guy, right? Maybe, I don't
Ага.
know. But see, but then location, orientation of this guy has nothing to do with the orientation to this guy, right? It has to do not only, well, it has something to do with it, but it also has to do with orientation to this guy, right? Of this guy. Because if this guy was from the back, then you wouldn't have to rotate. You just stay the way you were staying, right? If it's on the side, then you rotate it this way and then, right? So that will be what beamforming will be doing. But in order for the beamformer to make it doing so, you need some formal criteria. The Because simply listening to this guy doesn't work. Because there may be other sources, and you want to tune yourself away from these sources, okay? How to make the algorithm, how to make the simply, it's mathematics, it's nothing, it's just very simple mathematics, actually. How to make it understand, okay? Very simply, it's actually a pretty clever idea. The idea is this. Okay, again, x of t is our data. It's g1 s1 plus g2 S2 plus whatever, GP, SP of T. Okay, those are vectors. Okay, these are our data. Let's find W such that W transpose times G1 is equal 1, because I want to listen to source 1. This is imperative. This is you're saying I want to listen to source 1. Okay, and then, but also, let's do this. And otherwise, let's try to minimize the power of this guy. So this is the W times transpose X of T is simply some time series. Okay, simply some time series. You want to minimize the power, so the sum of squares of all these elements. Okay, so because you can say that Z of T is equal W transpose X of T, and then the absolute value of Z of T, the sum of square, the norm, is basically Z of T1 squared plus Z of T2 squared plus, and etc. Z of T capital squared. Okay, you want to, so basically you say that, listen, I want to minimize the power at the output of my beamformer. Okay, so that the power has to be minimized. Okay, unless you put a constraint, the solution W is 0, right? Here is your minimization of the power. Well, what's the problem? 0, that's it. Well, you say, no, this is not going to work. I mean, I want to listen to someone, okay? And then here is the guy I want to listen to. And you say that, okay, G1 is the guy. G1, it's a property of this guy, okay? So make sure that gain for this guy is 1, okay? And then after that, just minimize this power. But with the constraint that W transpose G1 is 1. Okay, so with this approach, you don't have to specify G2. You don't have to specify G3, GP. You don't care about them at all. You don't know what they are, but you don't care. You know, all you need to do is just, okay, now let's see how it's formalized, how it can be formalized. Okay, so
Can you say again why we have this constraint equals
because
to
I
1?
want to listen. I want, yes, here's the constraint. If I, let's say, X of T G1 S1, G2 S2, for instance, okay? Now, I want my W, and I want to listen, I want to recover S1, okay? So W transpose X is equal W transpose G1 S1 plus W transpose G2 S2, okay? If I want to recover this guy, I want W transpose G1 to be equal to 1, right? And ideally, W transpose G2 to be equal to 0.
Yeah, okay.
Right? But I don't know this guy, and therefore I'm kind of playing Pullman's version of whatever the perfect algorithm. I'm saying that, okay, well, do this, okay, make this gain 1. And how do I say that? Okay, there are other sources and you want to suppress them. I say, well, you know, and minimize the power. Okay. So, and then what basically what it is? Let's see. Assume that you have X. This will be just simple to understand. Assume that you have X matrix, right? So you absorb your X of T at moment T1, at moment T2, etc., at moment T capital. Okay, and those are vectors, right? Of the dimension number of sources. This is just a matrix, okay? It's a data matrix. The one that we plotted like with image scale or whatever, right? It's just a time series, okay? Now, your W transpose X will be a vector, right? So because you have W transpose multiplied by this guy, W transpose is scalar multiplied by this guy, another scalar multiplied by this guy to another scalar, right? So it will be Z, vector Z, but we will denote it as Z transpose, okay? Because it's a horizontal vector, it's not vertical, it's not vector column vector, it's a row vector, right? So therefore I put Z transpose because by definition, not by the convention, all vectors that we are dealing with are column vectors, okay? So that if you see something is underscored and it's not transposed, it is column, okay? All numbers of it are organized as a column, okay? And this is important because in vector algebra, you know, from which side you multiply, it matters. Okay, so so you have this z of t, right? And then what is the power of this guy? What is the power? Well, it's apparently it's z of t multiplied by z, right? Because it's z1, z2, z3, and etc. multiplied by z1, z2, z3, and etc. Right? And then it will be z1 squared plus z2 squared plus z3 squared plus etc. Agreed? Right? So okay, then we will take this and we will take this and substitute it in here. Okay, so you say that W transpose X, this is, and then Z, if this is Z transpose, then Z itself is transpose of this guy, right? So it's X transpose times W, right? Remember the story about the socks, right? That the socks are red sock, the blue sock. So X transpose times W, okay? Those are matrices, these are vectors. Okay, this is your power, and you want to minimize this, okay? You want to, you say that this is your goal, okay? You want to minimize this, but you want this W transpose G1 to be equal to 1. Okay, that's your optimization problem. Okay, so if you were in a if you only had two sensors, okay, if you only had two sensors, then you could have drawn this thing, okay, because what this is, okay, one more thing. You've gotten the data. This is the problem, that not the problem. This is distinctive property of this method, is that the filter, that the W, depends on the data. Okay, your data is X. They're already there. You got the data, and you are tuning your filter for this particular data. Okay, so you're exploiting the property of this data. You're exploiting the information about which sources other than G1, right, were present in this data, because depending on the constellation of sources, your W will be different, okay, because you will have to tune yourself away either from this source or from this source or from three sources together, or however, you know. So so anyway, yes, so if you assume that you have only what is M, right, M, two sensors, right, then you could have drawn this. Okay, I will draw it in a like looking from the top with level lines. Okay, so you have, this is your functional. Okay, this is your power. Okay, this is your power dependent. Yeah, and it's W transpose. It's a squared form of W, right? So it's W2, W1, and this is this. Imagine, right? This is like a parabola, right? No, not parabola, but how you call it? Paraboloid, right? So this is this surface, right? And this is this constraint. Let's say it is like this. This is your constraint. Equal 1. Because G is just a vector, so basically this constraint is what? W1 times G11 plus W2 times G12, right, is equal to 1, right? Those are your variables, right? V1, and those are just scalars. It's like AX plus BY equal 1, gives you a line in YX plane, right? The same here, right? So, and then your goal is to basically find W, which is this location. I know that it is location because if you imagine yourself this I don't know, here, this, right, and you look from the top, right, and you have some constraint here. So where will it have a minimum? Well, I mean, I put this way for you. Where will you have a minimum? Somewhere here, right? So that's exactly this, right? So and this is your vector W that you are looking for. Okay, so it has certain W2 and W1, right? This is your target, this is your goal, right? So, but of course you can't, you have many more sensors, and we need some analytical way to solve this, right? And this is the classical, it's called quadratic program. I mean, it's called program because all optimization theory, it's like linear programming. It's also an optimization method, right, to find a minimum of a linear functional. So in finding the minimum is called the linear program. Okay, the task of finding it is a linear program. Okay, so this is a quadratic program where you have linear constraint, and you want to minimize the variance at the output, because the sum of squares, it's you can call it power, but you can call it a variance, right? Assuming that it's zero mean, right? And then you sum them up, and those are zero mean guys. Then when you sum them up, it's just simply a variance, right? Dispersion, right? Okay, so and that's why this guy is called linearly constrained, because this is a linear constraint. Minimum variance beamformer. Okay, why beamformer? Because W is your beam. It's a beam, you know, it's a set of coefficients that forms the beam, which determines the direction at which you are sensitive. Okay, right? So now, how you solve this? Well, this is all pretty formal. Okay, so we will write W transpose X transpose W. You want to minimize this such that W transpose G1 is equal 1. Such that, okay, let's denote, let's denote, you'll understand why, but later. Okay, because I thought first talking to you about covariance matrices and blah blah blah, and then introducing this, but I decided not to, because we will see how naturals will come in. Okay, so you don't have to like bother about it first. So the important thing that X is your data matrix. Okay, you observed your data. Okay, so you listen to your data for some time, for some interval. Okay, and you have X contains some statistics, information about what's been there. Okay, and now you're trying to find a filter which will filter out the signal of interest for you. Okay, so this is your R. All right, and so you form so-called Lagrangian. Okay, Lagrangian, because to solve the constraint optimization problem, you do this. Okay, you say that so this is just it depends of W and lambda. Okay, and it is the original functional that you want to minimize plus lambda multiplied by the constraint, but the constraint you will have to rewrite so that W transpose G minus 1. Okay, it's just I approach it as a rule. Okay, I can of course explain why this is so, right? But just ignore it. Okay, it has to do with the fact that that the minimum, like the level line, will always be a tangential line to the minimum. Okay, so it always touches at a particular level line at one location, and from there you can derive this Laplacian Laplace whatever, I forget how it's called. Yeah. So and this is a scalar. You will rewrite it W transpose R times W, right, plus lambda W transpose G minus 1. Okay, well, this is the thing. You just expanded your optimization problem with, so you didn't know on the W's, and now you say, well, I have yet another guy that I don't know, is my lambda. Okay, lambda is where the minimum also occurs, right? So you have two sets of variables. You have W and you have lambda, but you approach it very formally, the same thing. You take the derivative of this guy with respect to lambda. Okay, so you say that, okay, so the dl for dw is equal rw, right, plus what is this, plus lambda g, right, g1 here, right, of course. So this is a vector, this is a matrix. Okay, this is, you agree, right, that this is, well, it's a vector derivatives. I mean, also don't if you're not familiar with it, don't, just trust me. Okay, you can always expand it and just make W to be W1, W2, W3, and G1 to be G1, G2, G3, you know, and then you can always take derivative with respect to each of these guys, and then sum them together, bring them together, and find that this is so. Okay, so this is the first equation, right? And you want this guy to be equal to 0, right? And frankly, you have to put here, right? You have to put 2 here, right? Is it right? You can see, just because it's a square, right? Yeah, so it's 2, yes. Okay, so 2rw plus lambda g is equal to 0. And then the other thing, this guy has to be equal to 0. And dld lambda, because this is your another variable, right? Because at the point that you're expanding your functional, now it used to be only a function of w, but now it's function of w and lambda. And of course, the derivative with respect to all w and lambda has to be has to be 0, right? So
Sorry,
yeah,
small quick question. What is lambda?
it's a Lagrange multiplier, okay, whatever. It's a Lagrange
It's
multiplier, whatever. Just keep it this way, okay? It's a Lagrange
okay.
multiplier. It's the how to say? It's basically it determines the location of this constraint, depends on the location of this constraint with respect to your function, okay? Well,
Okay, thank
but
you.
you find it from, and it's, I mean, well, it's a separate big lecture. It's like it can be very well introduced from the dual optimization, there's like primal optimization problem. There's Daniel, maybe you will switch off your microphone, because otherwise we hear.
Is it my microphone?
I don't know.
It's someone
Somebody is speaking on background.
But I thought it wasn't mine. But
It was somebody speaking in Russian, maybe. Well, anyway, forget it. Anyway, so but you were gesticulating, so I don't know. And when we speak, our motor cortex works. All right. So yeah, so therefore you just have to also take the derivative with respect to this Lagrange multiplier. And if you have multiple constraints, then you have multiple Lagrange multipliers. You have like 3 or 4 of them, okay? But you know, just approach it at this level, just approach it mechanically, okay? And clearly the derivative with respect to lambda gives you this guy, right? And making derivative with respect to lambda will make this guy -1, and you want this to be equal 0, right? Right? Because this guy doesn't depend on lambda. The only thing depends on lambda is this one, and lambda is just simply a number, like just x, right? Multiplied. So you just take the, okay. So from this, what you do, you first express w from this guy, okay? So you just, let me see. So yeah. So you express w from this. You say that from this first equation, okay? So you take this first equation and you say that w is -1/2 r minus 1 g, and then I forgot lambda, okay? Okay, agreed? So it's your w. But of course it depends on lambda, and it's not yet a solution. So now you take this guy, which is your w, right? And you substitute it in here, okay, in order to find the value of lambda, where lambda and w together will make you happy, right? So that you substitute this guy in here, and you get -λ/2 r minus 1 g transpose, right? Multiplied by g is, and then -1 is equal 0, right? Then you take -λ/2, it's a scalar, right? Then you take g transpose r minus 1. R is a symmetric matrix, right? So you don't have transpose of it itself, right? So g is equal like -1, right? Is equal 1, right? And then from here you can find lambda. Lambda is equal 2 divided by g transpose r minus 1 g. And of course g1, right? We are interested in g1, right? This is g1, okay? G1, yeah, okay? So, and then you basically, all you do, now you say, okay, this was my solution, and this was my solution, it depended on lambda. I found the proper lambda, okay, which satisfies together my constraint and correspond to the minima, okay? So therefore I substitute it here, and you arrive that your W is equal R minus 1 G, okay, minus, I forgot minus here, right? Because minus is here. R minus 1 G divided by G transpose R minus 1 G. Vector, vector, matrix, matrix, vector, okay. So, and this is the expression for the linearly constrained minimum variance beam former, okay? So let's see what the difference between what we have already seen so far and this animal, and let's see how this animal actually is working. Okay, let's first see how this animal is working. Okay, you will very often arrive at solution if you do some sort of optimizations in our business, right? You very oftenly arrive into constructs that look very similar to this one. Okay, the main difference between them will be the content of this guy. Okay, the content of this R. This R is covariance matrix. Okay, why it's covariance? Because we assume that our time series are zero mean. Okay, therefore, if we compute the expectation of the product of two time series, we'll get either variance if it's on the diagonal, right? Or we will get a covariance where it's x1 times x2 and mathematical expectation of these two, right? Because means are subtracted. Okay. Therefore, it's covariance, they covari. Not how they're related, not correlation, but covariance. Okay, how these guys covari. So R, if you remember, was simply, in our simple explanation, was simply XX transpose, right? Right? And this is in fact not covariance. It's some surrogate tool. Okay, it's something that you use in practice though. But this is formally not a covariance. It's its estimate at best. Okay, and I also forgot to divide by n by t by the number of time slices. Okay, but it doesn't. You don't have to. I mean, because for the fixed number of time slices, the minimum for R will be the same as the minimum for 1 over T R, right? It really doesn't matter. So, but let's look at this guy and see what it means. Assume very simply, assume that you have X, which X matrix X, which is first time series observed during T time slices, and the second time series at another T sub time slices. So this is your X, okay? So now X transpose, if you multiply X transpose, then you will get this. You will get sum of X1 I, or I goes to T xi squared. Agreed? Because if you substitute, if you add this guy here, x11, x12, x1t, and x21, x22, x2t, right? So then this diagonal element here will be this guy multiplied by this guy, right? Which is a summation over this index of these two, right? So it's basically sum of x1i times x11 squared, x12 squared, x1t squared, and etc. Okay, so here you will have summation again over index I, which is time index, x1i, x2i. Okay, because this guy is multiplied, this guy is multiplied by this guy. There's the activity of the first sensor is multiplied by the activity of the second sensor. Okay, and then similarly here it will be x2i, x1i, which is like in our case the same thing because they just changed to the symmetric, and then you will have x2i squared. Okay, and if let's put 1 over 1, not sorry. Let's put 1 over T here, okay? And let's put 1 over T here, okay? And let's remove this. Okay, just for strictness, okay? Because T it's just a constant, right? Okay. Then this tells you 1 over t sum of x1 I squared, given that x1 is 0 mean, right? Then this is simply sigma 1 squared. So variance of the time series, okay, of the first sensor, right? Agreed? This one correspondingly variance of the second sensor, and this one is the covariance, okay? How they cover I, right? Average product, right? So this is, you probably encountered it many times, right? But that's your covariance matrix, basically, okay? That's the covariance matrix of your data. This is, of course, in our case, it's an estimate because we use the finite sample of data. We use this to estimate the statistical structure of this matrix, right? Of this data, of this two-dimensional vector in our case. In practice, of course, you have many different ways to estimate this W, right? There are this covariance matrix. There are smarter ways. There are more stupid ways. There are ways that use some priors. There are many different approaches, but the essence doesn't change. Okay, it's a covariance matrix whose diagonal contains the variance of the corresponding random variable, and the corresponding off-diagonal elements, like element 1, 2, is the covariance between the first and the second vector. Okay, so now, so yeah, this is your covariance. Okay, so now assume let's no again, see again, I was so happy, but now I'm not. Again, is it time for a break? Because then I will have time to reboot.
Yes, it's time for the break.
It's time for the break. Okay. Yeah, almost. Yeah. All right.
But,
Yeah, let's reboot. Let me give me a break. I will reboot this piece of
but
crap.
can you can you scroll
No, I can't.
where we were?
That's the problem.
Ah,
I can't. It's frozen.
ah,
It's frozen, and I can't do anything. You know. See, that's it. You know, that it doesn't change anything. You know. So,
okay.
yeah.
Then
There we go.
I would just ask.
Something
I
changed.
will-
Something changed. Yes, I can scroll. Okay, now I can scroll.
Oh, here from так, вот это вот W, я не поняла, из какой формулы сюда подставили.
Где?
Лямбда подставили, вот где W последний, вот обведенная формула.
Вот
Мы
это?
ее...
Вот это? Hold on.
Да, вот эта формула. Мы сюда поставили лямбду, но куда-то...
Вот это, да?
Так.
Вот. This one, right?
Нет, конечная формула W.
This one.
Да, this
Okay.
one.
Okay. We take, see, we took this guy, we took this guy. From this guy, we found that our W has to be R minus 1 times G, okay? Multiplied by lambda, okay? And okay, we don't know lambda. And lambda, and we need to know where on this thing, you know, to determine the lambda, we need to substitute this W into this constraint. Okay, so
yes.
This is like, you can say, the parametric form of our W. Substitute this parameter, and once we found this lambda appears to be this way, this guy, we substituted back to this expression, okay, and we arrived at this expression. So we took this lambda, we substituted to this guy. So it's like, you know, it's like x plus y is equal 3 and y minus x is equal 5, for instance. Okay, you say that, well, x is equal 1
yes,
minus 5, right?
I understand. I'm thinking about this
then,
W formula. Here we have covariance matrix transpose, and in the
inverse, yes,
inverse, yes,
yeah.
And in denominator, it's inverse.
It's G transpose R minus 1 G. It's a quadratic form with so you have R, you multiply it from the left, you multiply it from the right, and so you get a scalar. This is a scalar.
So okay. Okay,
Yeah?
thank you.
Yeah. Okay. So see, I can scroll. Yeah. Oh, that's pretty cool.
Все,
Okay.
проблема решена.
Yeah. Well, I don't know. I mean, but I don't know now. For now, they are, but you never know.
Ага.
Okay. Let's have a break until what time is it now? Now it's 17:43. Let's have for 15 minutes. Okay. I'll start at 6.
Окей. Окей, thank you.
Okay.
Okay. Thank you. Hello. Are we back?
Yeah.
Okay. Everybody? 8? With me? No, 7, because there are two of me. And two of Daniel, then 6, okay. 6 selected fighters, okay. All right, so let's continue. Yeah, there is a good news for you. And for me, by the way, we have 3 lectures. After this one, we have three overall, 3 classes, 3 not lectures, but 3 classes. Okay, so most likely we will do it this way. Next Tuesday, I think we have a class, right? And I will give you a lecture on next Tuesday. Okay, and then Dasha will held 2 seminars on Friday next week and Friday week after. Okay, maybe I will intervene at some point, with maybe like an hour or something of some lecture material. Okay, but we frankly have we have beamformers, and then we have minimum norm kind of estimates where this rightmost in, right, where we assume that all sources are distributed, and then you all have to do is to practice it with Dasha, with all the seminary Python or like brainstorm or whatever. Okay, so yeah. All right. So this is the, let's see. So this is the covariance matrix, right? Now, there is one other thing that you need to understand before we are going. Да что ж такое-то? Hold on. Oh yeah, I know what helps. Okay, if you do it this way, then this piece of crap starts scrolling. All right. So another thing you have to understand is this. You know what? Well, we need to be speaking about random variables. I'm sorry. I mean, we just because the speaking about covariance is the first step here, right? So, if you have a random variable, let's say x, right, and it has certain covariance, let's say r of x, okay, if you in the simplest case, if your r of x is simply equal to identity, okay, then and in case x is only 2-dimensional, okay, dimension is equal to, then you can draw it like this. You can draw a scatter plot of this variable, okay. Typically we deal with Gaussian random variables, so they're kind of spherical, thin, like this, like they equally likely distributed with respect to the distance from the origin, okay, and each point is the observation, okay. For instance, this is x1, x2, the first observation, this one x1, x2, the second observation, and whatever. This is x1, x2, nth observation, okay. And so they form something like this, where there is no preference of the direction. This is x1, this is x2. You can't say along which of the directions this variable likes to group, right? Or maybe not direction, maybe some line here, right? Whereas constantly, on the contrary, if you have in the case where r of x is, let's say, not identity, but let's put it this way, it's one here, and 0.6 here, and 0.6, of course, it's symmetric, right? Then if you draw it, you will see something like this. Okay. So x1 again, x2. So you will see this preferential direction. Okay. And it will be it will correspond to this correlation of 0.6, the extent to which these two guys are not along the single line. The higher this correlation, the more the scatter plot will look like a single line. Okay. So it will tell about if you have, like, let's say if you have 0.9 here, 0.9 here, then you'll have something like this, like along a single line. Okay. Look here. Okay. Right. So and there is one thing, so you can think of this, like, try to imagine this. Okay. You can think of this if these points, they are some, like, noises, samples of noise coming into you, right? If you're trying to listen to something, if you're standing in the center here, and in this case, they're coming from everywhere. Okay. They're coming from every distance and from every location, right? Well, the distance, not so much, because the closer you are to the center, the more of them are coming, the further away from the center you are, but you can't move away from the center. Okay. Assume. And the only thing you could have tuned is just trying to find the direction into which you look to free yourself from the bombardment of this noise. Okay. Right. So and therefore it's very simple in this kind of environment where the noise is white, right? It's very simple to make a strategy how you behave if you want to listen to the guy that is in this direction. Okay. You just simply turn yourself to face this guy. Okay. You face this guy directly and you listen to him, right? And why? Because if this guy stops speaking, you will not be able to, from the amount of noise that coming into your ears, you will not be able to say which orientation you're turned at, right? Because the noise is the same for all possible orientations. Okay. So therefore the best strategy is simply to tune to this guy of interest. Okay. If you are in the environment where there are potentially several such guys, okay, for instance, okay, and you don't know where they are, these guys are basically becoming noise, right? These guys are becoming like parts of noise, but the presence of these guys makes this noise already not spatially wide, right? This noise is you can no longer say that this noise is the same in all directions, right? Because if you keep rotating, you will be listening, you will be hearing that once you're passing when you rotate and you pass in this guy, then you will see increase of loudness, then decrease again, then increase again, decrease, and etc. Right? So it will be not even spatially, right? And therefore, it will be very difficult to make any kind of strategy if you want to listen to this particular guy, to some specific guy, right? Because you need to somehow take into account the information. Why every lecture I get the call? So you have to listen to you have to take into account the fact that these guys are present here. And how to take this into account? Well, Beamformer gives you this recipe. I'll explain you now. Just a second. In order to be able to understand further, you need to know one other thing. There is such thing like called whitening. Okay, so if you have distribution like this, where clearly x1 depends on x2, right? You can't say that x1 is independent on x2 because you can predict from x2, you can quite well predict where x1 will be, right? If x2 is here, then x1 is most likely somewhere around this guy, right? As compared to this case, where you can't predict anything from x1, right? Because x2 can be anything, right? It can be, if your x1 is this, then x2 can take the range of values from here to here, right? Right. So, and therefore you there is such thing called whitening. Okay, what you do with whitening, you simply turn this picture into spherical picture again, but you do it mathematically, you do it artificially, you do it virtually. You kind of place yourself in the space where the interference is spatially even, okay, but there is no preference, spatial preference at all. And in this new space, it becomes very well clear how to tune to a particular source, right? You just simply turn yourself to the source, except that your units and your measurements that you're tuning to the source will be different because you're in different space. You transform the space somehow, right? You stretched one axis, you squashed another axis, you did some rotation, whatever, right? So, and how to do it formally, it's very simple. Look, x is your random variable, okay? Sorry, x is your random variable. The covariance matrix of x is mathematical expectation x transpose, right? Where x is your vector, right? So it's basically mathematical expectation of x1 x2 multiplied by x1 x2, right? This is mathematical expectation x1 times x1, x1 times x2, x2 times x1, x2 times x2. Okay. Okay, this is your mathematical expectation of this is basically a covariance matrix of your x, right? And you can replace this if you feel more comfortable this way, x1 squared e x2 squared x1 sorry x1 x2 here e x2 x1 and here x2 x2, okay, or x2 squared, right? x2 squared, okay. So basically remember that this is very similar to this guy, right? This is this guy, right? Because we just simply replaced the operation of expectation with this, something that you can compute in practice, right? That you can take the summation of the samples and division by the number of, examples, right? You just simply compute the average of this quantity, right? That's exactly the same thing, except that I replaced the estimation, where I take the summation and divide by n. I expect by the more high flow mathematical operation of expectation. Okay, and then if you take if you look at what will be the assume that you take your y variable and you multiply y by some y obtained by multiplying x with some matrix A. Okay, in the simplest case where A is identity, then your Y will be exactly equal to X, right? In the more complicated case, you transform X somehow, right? You simply multiply. Let's see what will be the covariance matrix of Y if we know the covariance matrix of X. The covariance matrix of Y is expectation of this product, right? It's Y1, 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 Y2, Y2, Y1, Y2, Y2, right? So let's substitute it. It will be A X transpose A. Agreed? So I just simply took this and substituted in here. And I took the transpose of this and I substituted in here, right? So this is X transpose A transpose, right? Right? And then I took the expectation here, right? Because, well, A is not a random matrix, right? A is some deterministic matrix, just a set of numbers, okay? And X is your random variable, right? Therefore, you can take the expectation and apply it only to this guy, right? Because it will be just simply a those are just scalars, right? Scalars and summations. So you basically can write A times E XX transpose A transpose. Okay, this is a matrix, this is a matrix, this is a vector. Okay, so and that means that this is simply A times Rx times A transpose. Agreed? Agreed or not? Did you follow, please? It's simple, but I mean it requires some linear algebra, basic linear algebra thing. Hello?
Yes, yes, it's clear.
Ah, okay, cool. Very nice. I'm glad. So anyway, so basically it shows you that you can shape the covariance matrix and you can change the covariance matrix of a variable y by adjusting a in a certain way so that the covariance matrix of y is different from that of x, right? Now assume that x has some covariance matrix and it's not identity, but you want y and you want it such that you want that the covariance of y is identity. Okay, just want this. Okay, you want to whiten, it's called whitening the data, right? You want to whiten it. Well, then it's clear you can select a to be equal rx minus 1 over 2 square root of this matrix. Okay, don't bother what it is. Square root is not the square root of each element of matrix, of course, but it's just some operation. You can in MATLAB you can say that inv sqrtm of r, and it will give you the inverse square root. Okay, so and therefore you have, if you substitute this into this expression, then you get y transpose expected value is rx minus 1 over 2 multiplied by rx multiplied by rx minus 1 over 2. It's transposed, but rx is symmetric and its square root is also symmetric, right? So, and that will give you identity because it's like it's if you put it into scalars, it's just some z multiplied by 1 over square root of z multiplied by 1 over square root of z. It's 1, right? But it's just a matrix. But I mean, we don't use just 1 over. We use inverse square root square root of the inverse of the matrix. Okay, so therefore we can whiten the data by multiplying the data by the matrix that is equal to the inverse square root of the covariance. Okay, and that's a very general recipe. Okay, you can always whiten the data. You can always take the data which have dependence and you can always whiten them. Okay, this is a classical approach, and it's a foundation of many methods, and you can actually explain how many different methods, how they behave and why they're so behave so if you use this whitening argument. Now, let's look at our beamformers. Back to the beamformers. Our beamformer, if you remember, I do, it's r minus 1 g divided by g transpose, sorry, r minus 1 g, vector, vector, matrix, vector. This is our w, okay? This is our vector, remember? And this vector had this property that it will have gain 1 at location g1 and will provide the minimum power at the output. Let's see what it does actually. This guy, how do we process it? We in order to extract the estimate of activity, we apply this guy to the data, right? So we multiply this in order to obtain S of t. We multiply this guy by the data, right? So look what happens. We are taking G transpose R minus 1, okay, multiplying by the data X of t. And we are dividing by G transpose R minus 1, G1. Agreed? This is just a scalar, right? And for each time slice, this is also a scalar, right? For each t. So we have many of such elements, right? Now, let's represent r minus 1 as r1 minus 1 over 2, r minus 1 over 2. We can't do this, right? Why not? I mean, it's a covariance matrix. We take a square root of this and inverse square root and represent it this way, okay? And then let's rewrite it. S1 of t is equal G transpose R minus 1 over 2 multiplied R minus 1 over 2 X of t divided by G transpose R minus 1 over 2 R minus 1 over 2 G, okay? Right? And now assume that you are simply in a different space, in a space transformed with respect to square root of the covariance of your X, of your observations. So assume that you are in the space where your measurements are called Z of t, and they are simply R minus 1 over 2 X of t. And the topography of your target source that used to be G1, is in this space. It's also transformed, right? Because if you turned yourself, or if you scaled everything, then you also have to scale the rest, right? If you are in a room, if you scale the size of your room, then you also have to scale this furniture, right? Somehow, right? If you want it to be, if you want topological stuff remain the same, right? Then you have not topological. Don't take this like literally, but if you want things to be similar, right? Then you have to scale your furniture, right? Well, the same thing. So if you let's say if you stretched one of the coordinates, then in order to explain that you have to make you have to go to the particular object, you have to make more steps along this stretched dimension, right? So you have to also extend your directions, right? You say that you used to go one step forward, one step to the right, one step forward, one step to the right. Now you go one step forward, two steps to the right, one step forward, two steps to the right, because my right direction is twice as long now. And your object that used to be there, it's shifted with the space to that location, right? In order to arrive to this location, you have to scale your directions, and your directions is G1 if you talk about the source, right? So, and then your what we call it, let's call it G1 wave tilde, okay? And substitute this into here. Very simply, then you say G1 tilde transpose multiplied by Z of t divided by G1 tilde by G1 tilde. This is trivial, right? All you're doing, you're taking your data in this new space and simply projecting it onto the target topography, on the topography of the source that you're interested in. Obviously, right? Because you're now facing the guy you want to listen to in this space, in this transformed space. And this is just a scalar, right? This scalar is just to make sure that you get unity gain constraint, right? Remember when we had when we were doing estimation of sources, we had x of t, it was equal G1 S1 of t plus noise, right? Whatever, doesn't matter what was in this noise, right? And I said that in order to estimate S1 of t, remember in this even MATLAB script, we had W, which was equal G1 divided by G1 squared. Remember when we were minimizing these cosines, remember that was this, right? But isn't it the same as this? It's exactly the same, right? It's just in this is in a different space, in a transformed space where we took into account the spatial covariance structure of this space. Okay, so basically what happens, you are see, you can also think about it this way. Okay, see, you are in the space where there are sources, and they are in general unevenly distributed somehow. Okay, you want to listen to some particular source. The recipe is this: take all this power in this space, all, and distribute it evenly in all directions. Then it will be like something non-uniform will become, you know, in every direction you will have some power, but it will be the same in all directions. And then simply turn to the source, at the location of the source you want to listen to, at the direction of the source you want to listen to. Okay, because the only thing you can do, the best thing you can do is, now once you distribute it everywhere, you have to simply look at this direction. Okay, You should have to minimize the cosine, maximize the cosine of the angle, right, between you and the source. Okay, and that's basically explanation why how the beamformer works. Okay, nothing. There's no magic. Okay, it's all trivial. It's all because it's all, come on, it's all second order stuff. It's really boils down very often to very natural explanations. Okay, but see, the point here is that you are in the beamformer business. We are in the beamformer business because we don't know where our sources are. Okay, of course, if you know where the source is, for instance, your G1, right? You know your, and you know the noise, you know the structure of noise, you know the for instance, you recorded the data. Okay, you can in MEG, for instance, right? We have two noises in MEG. Instrumental noise, right? Where you can record without a subject. You just remove the subject, you record in MEG like for, I don't know, for an hour or something, right? And you can estimate this noise covariance from there, right? From this data. You can, second level of noise is subject's brain noise, okay? Subject is not involved in any task. He's not like solving problems, not watching videos, not whatever, not doing anything, just sitting and resting. And you have this noise, which is brain noise, which definitely have uneven distribution of sources. You know, it has some, like, of course, very complicated structure. But then you can take this noise and take its covariance. And then you take this very subject, you place him or her, and you ask him or her to solve the problems, okay? And then in this case, the subject will have certain sources that are active. And you are, for instance, assuming that there is only one source that is active in this, only one. This is unrealistic. But if you're assuming that the one source and you know where it is, you want to listen to it, then of course you don't have to use beamformer because beamformer is not optimal. You know why? You know noise, you know one source where it is located. All you do is this. But you do very similar anyway. You're doing this. You are looking at this expression again, x of t is equal g1, this only source, plus this noise, okay, n1 of t plus n2 of t, okay? So two noises. The first noise is your brain noise, and the second one is your instrumental noise, right? Then you say, because you have them, you can estimate noise covariance matrix, right? Why not? You have x transpose, right? N transpose, okay? And then again, how you take into account, how you make clearly G1 x of t is not divided by G1 transpose G1, although formally, if you substitute it here, right, divided by G1 transpose here, then you will substitute it here, G1 transpose G1, right? Then you get unity here, right? This is very good. But a lot of stuff will leak from these guys, right? Because they are different at different angle, at different corners. They're not. What is this? But hey, Bakare, hey, please turn on your mic. There we go. Okay, I muted him. Good. All right. So anyway, so you understand.
Sorry.
Sorry?
I'm sorry.
I'm
sorry for the
You are sorry. Yes, you should be sorry. Yes. All right. So anyway, but the bad thing about this approach is because if your noise would be white, then yes, this is a proper way because regardless of what G is, noise will be the same in all directions, right? In all locations. But noise is not white, as I mentioned, because noise is instrumental noise plus brain noise. You have alpha rhythm, you have sensory motor rhythm, you have, and it's like very well spatially organized rhythm, right? Activity. Therefore, what you have to do, you just say that you whiten your data. You whiten your data minus 1/2. It will be R n minus 1/2 G1 S1 of t plus eta of t, and this noise is white because you've selected R to whiten these two noises, okay? You just sum them up and you whiten, right? So, and then you say that in this scenario, my proper processing will be indeed multiply by this source topography, which is Rn minus 1 over 2 multiplied by G, the source topography, but in this transformed space. And then if you write this whole thing, you will arrive at exactly this guy, except that instead of R, which used to be the entire data covariance, it will be just simply noise covariance, okay? And this is not a beamformer. This is so-called maximum likelihood estimate. I'm not going to tell you why it is so, but this is not a beamformer. The difference is that the matrix R in the maximum likelihood estimation, R is noise covariance. In beamformer is your data covariance, okay, which contains the source of interest, okay? But because you don't know what the source is, okay? So, and you don't know, not so much that you don't know where the source is, but you also don't know where the noise is, what are the noises, and etc. Then you use beamformers. Of course, you can reformulate beamformers in cases when because see, you never have a single source. You always have multiple sources, right? And all you have to do, you have to somehow distribute the degrees of freedom that you have, your 100 sensors, right, or 200 sensors, 100 degrees of freedom, in order to not only emphasize the source of interest, but also suppress the interference sources, right? Okay, and so see, and the beamformer, what it does, beamformer, you can loosely think about beamformer this way. Beamformer, like if you want to rhetorically describe to someone what was the lecture today about, okay? So, okay, it was about some method that listens to the data, understands where the sources are in this data, and attempts to find such a spatial filter that appears to be blind to the sources, yet emphasizing the source of interest, okay? So this is correct and not correct at the same time, because when you say blind, it's not exactly blind, okay? Because there is still variance that will be distributed along the entire space. It's not zero, okay? So it's some variance, but it will be the same. It will be the same in all directions. You know, this, and what it will distribute something, it will extract from the data. Therefore, it will be spending its degrees of freedom not to cancel all possible sources, but to cancel only those sources that are present in your data. Okay, and that's why you get super resolution, so-called super resolution properties of the beamformer if you use it in the scanning mode. I will show you what it is, or even not even the scanning mode. You can say that you want to listen. Let's say you want to listen to a source that is located here, and you want to listen to a source located here. If they're close enough, then it might be very difficult to listen to this guy and not to listen to this guy. Okay, but with beamformers you can do it because you can because you will not be trying to cancel this source, this source, this source, this source, but you will only be working with these two sources, trying to tune yourself away from this guy and some noise, and tune yourself at for this source, right? So that's a general idea of beamformers, okay? It's so far it was very simple. It was LCMV with a single constraint, linearly constrained minimum variance beamformer, and it was for a scalar, for a single topography of a source, right? For a single, like with a source with a known orientation, right? So it's just single vector, right? What if you don't know the orientation? Okay, what if you just simply don't know the orientation, and you want to make a beamformer that is sensitive to all three directions? Okay, how do you do it? Well, very simply, the same way. So you say that, okay, your x of t you observe, and it's some g s1 of t plus some noise, okay, and maybe some other sources, but you know, it's anyway the same, the entire covariance of the entire matrix or for the entire data, right? And then you say that you want it's so-called a vector beamformer, okay? So we will create three beamformers, okay? Three vectors. One vector wx will be sensitive only to the source located at location at location 1, okay, but oriented along axis x, okay. We want this to be 1, but we want for this guy, GZ, we wanted to not to listen to the source that is at this very location, but located along Z, and we don't want it to listen to the location to the topography Y. Okay, so we have three constraints here. Got it? So and then you have vector, this is Wx, you have vector Wy. In this case, you have Gx equals 0, Wy, Gy equal 1, and Wz, Wy, Gz equals 0, right? And you have Wz, which is also Gx will be 0, Wz, Gy will be 0, and Wz, Gz will be 1, right? All right. So we have three vectors.
Mhm.
For each vector, we have three constraints. So in fact, we have three beamformers, but we will be looking for them simultaneously because they're all connected, okay? So we have basically only Gx, Gy, Gz is a set of topographies, and we want our vectors to be, so we can rewrite this constraint as simply W times G, where G will be Gx, Gy, Gz, right? Equal 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. In other words, W times Gx, Gy, Gz, transpose, of course. And it's equal 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. And V is now a matrix. It has three elements, right? So it will have, like, again, Wx transpose, Wy transpose, Wz transpose, multiplied by Gy, Gz, and is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so W transpose times Gx is 1. W transpose times Gy is 0. W transpose times Gz is 0, and etc. Okay, W transpose Y X is 0, Y is 1. Okay, but formally you are in exactly the same setting. You want to minimize, but the only problem is that the only thing is that you are, in order to say what you want to minimize, you need to use this trace operator, okay? Because you need to sum, because see, if you multiply W my matrix by your X, right? You you will get 3 time series, right? Right, because this is your vector, this is your matrix, and this is x of t, right? You get for each of these guys, this is a vector, a vector, a vector. For each of these guys, you will get a time series. So it will be 3 time series, each corresponding to the activation of your source, of the corresponding to a dipole oriented, let's say, along x, y, and z directions, right? Wx, Wy, Wz. So let me try to explain this. If your source is not rotating dipole, if your source has fixed orientation, right, then always, I mean, up to the error, of course, always you will have the same ratio of power of the signal that you estimate with Wx times your x, Wy times your x, Wz times your data x, right? Because it just simply will be a coefficient, right, which tells you about the orientation. But if these coefficients change every time, then it means your dipole is somehow rotating or moving, maybe, just moving, but you're assuming it as a rotating dipole, right? But it's kind of moving along the gyros, or along, let's say, if you take a cortical surface, piece of cortical surface, and if you have dipole here, dipole here, dipole here, but relatively poor resolution, spatial resolution of MEG, you are beamforming at this location, but you will be seeing it as a dipole that is first oriented along this direction, here oriented in this direction. So it will be kind of, it will be every time slightly different dipole located in one location, but with different orientations, right? With slightly breezing, the orientation is moving. So anyway, so this is your this is your this is your uh, uh, this is a formulation of the scalar beamformer, of the vector beamformer, and you want to say that here. What you want to say? You want to say that it's equal to identity, right? No, sorry, it's not this. Let me scale. Let me remove this. Remove this and make this formulation. And then you want to say that W transpose times X, right? Let's assume that this is a matrix. This is a matrix, and then this is a matrix. And it was tempting, we were tempted to say that this is minimized, right? Well, not this one minimized, but only the diagonal is minimized, right? The sum of the squares of the diagonals of the time series on the diagonal, right? So therefore you need to write the trace. Trace of this is minimized. Trace is the sum of the diagonal elements, okay? So it's a power, but on the off diagonal elements, you will have correlations of the estimates of activity along of the dipole oriented in x direction and y direction, x direction and z direction, and etc. Right? But you're not interested in this. You're interested in minimizing the power, right? So yeah, I will take it. I had these notes here so that because that will be. I don't want to confuse the order in which we multiply the matrices, but otherwise it's all pretty much the same. Yeah. So and then we have our constraint where W transpose G, where G is a matrix. This right. Is equal to identity matrix, right? And more generally, we can say that we are not. Maybe we want to emphasize the dipole along some specific direction, right? Or maybe we want some more complicated constraint, right? So for for the to make it general, we can say that it's equal to some C, right? To some matrix C, which is your constraint matrix, right? And now I just realized that here it's not. Well, anyway, yeah. So we will do it. So here, so we do exactly the same thing, right? We write W transpose XXW plus lambda multiplied W transpose G minus C. And now our lambda is a vector, right? Because
Can you say again why we minimizing only sum of variances and
because we are not because we don't want to minimize the covariances. We want to minimize the output power.
Okay.
So because if we were to take this, and it actually turns out to be that this trace you can simply expand it as W x times whatever plus WY and plus WZ, and it just don't pay much attention to the trace is important, of course, but it actually simplifies things, okay? Because when you take the derivatives, taking the derivatives of not when there is no trace here, much more complicated, okay? So that it's just so we'll put it here. We'll put trace this guy, okay? So and basically, this is something that you can prove when you take the derivatives of the trace. It will be exactly the same as taking the derivative of this guy, assuming that you're only interested in the diagonal elements on the diagonal elements of this matrix. Okay, so and then you write and x, your estimate of the covariance is your here, right? Your x transpose, your matrix, right? The same thing. So you can rewrite this as a trace of W transpose R W squared plus lambda transpose W transpose G. Sorry, there's a goofed here. Here, minus C, right? Minus C. Okay. So and then you again do the same thing. You take the derivatives. You take and this is your L of W and lambda. Okay, W matrix lambda. So and then you say that okay, very nice. You take 2 RW, okay, from this guy plus lambda transpose G. And now it's a matrix equation, right? So you have a set, and this is a set of equations. This is not a single equation, but this is a matrix, this is a vector. This is a vector. This is right. So, and then you take the second equation. If you take the derivative with respect to, so this is dl dw, right? Very similarly, but like symbolically, it's almost exactly the same. D lambda, you will get simply the constraint minus c equal 0, right? And this, you're equating it to 0 because you want the maximum, right? You want the extremum of this, or minimum, minimum in this case, right? We don't prove that it's a minimum, but because the function is quadratic and it has positive coefficient, then of course it's got this guy is a covariance matrix, and covariance matrix is a positive definite thing, therefore we'll have this kind of shape, and the only extremum is a minimum, right? So and then from you can substitute and do exactly the same what you've done, and what we have done, and then we will arrive at this. Your matrix W will be, I will just copy it so not to waste time, R minus 1 C multiplied by C transpose R minus 1 C minus 1 so yeah, G, sorry, this is G of course, and then multiplied by matrix C, which is your constraint matrix. Let me write it properly here. So this is G. Okay, and that's your solution. See, it's exactly the same as we had it before, right? Here, formally, very much the same, right? Here, except that we don't have any more, this quantity is not a scalar anymore, right? And therefore we have to take inverse of it and multiply our R minus 1 G from the right? And we don't any longer have single G, we have a matrix G, but conceptually things didn't change, okay? So you again have your vector W that when applied to your data matrix of the set of vectors, right? We applied to your data will give you estimate of Sx of t for the first source, Sy of t for the first source, and Sz of t for the first source. Okay. So, and take into account, of course, the entire covariance structure of your data, which is stored in R. Okay. And this is so-called a vector beamformer. Okay. Vector beamformer. Okay. So, are you with me?
Yes, can you say about the matrix C? What is it like?
This matrix here. Let me show you.
Yeah, from constraint.
Yes, from constraint. Yes. Here.
W-
Just
where is
because see, you want what do you want? You want two estimators, right? You want three estimators. You want WX,
Yeah.
WY, WZ, such that one guy is listening to the dipole located at location 1 and located perpendicularly, oriented along x-axis, right? And you want to be, for this source to be blind, for this filter to be blind to the two other directions, okay?
Yes.
So therefore your constraint is 1, 0, 0, okay? So WGX, WGY, WGZ on the row. The first row is
Yeah.
GX,
Okay.
then 0, then another 0, okay? This is the story about this guy, the first guy, okay? Then similar story about the second guy, except that you want it to be sensitive to Y direction and not sensitive X and Z direction.
But so why you don't try just identity matrix? What's
That's identity matrix. Why not? Okay, why not identity? Well, because there may be different situations, okay? Because you may be wanting for some reason somehow to emphasize activity from X, okay? Then you put 10 here and put 1 here, 1 here, okay? Or maybe in MEG, for instance, you are not interested in the third direction, which is radial. For instance, you have oriented your dipole such, your forward model such that this guy, the third direction is a radial direction. You don't care for the radial source. Or on the contrary, you may want to listen to the radial source. You want to prove that you can see radial sources in MEG, okay? And then you put zeros everywhere and one here.
But so there is no any constraints like normalization constraints that they should sum like rows should sum up to one or something. No, nothing like that.
For this, no. For this guy, no. No,
Okay.
no.
Okay.
No, for this guy, no. It's see it basically it's the role of the C matrix. It's in the very end. You are simply collecting these solutions. Okay, it's not it's really it's but identity matrix. It doesn't even change anything. Okay, yeah.
Mm-hmm.
The important thing is that you are optimizing all of them together and not separately. Therefore, this G has topographies of all three guys, so that you have a chance of canceling the other two, right? So that because if you were to separate to estimate them, you can make a beamformer just for GX separately. You can make a beamformer just for GY, and you can make a beamformer just for GZ separately. Okay, for three orientated for, but this way you will not guarantee that the beamformer is not listen along GX will not listen to the locate to the Z to the Y axis, and in here you guarantee, okay, because you are inverting it all together, right? Because you're again, this is the same story as I started today, not because of the just some coincidence. I started from the story when we have G1 S1, G2, S2, G3, S3, right? Where we have matrix G times S, right? And this is your X, right? I didn't start it just by chance because I showed to you that basically very same construct G transpose X times S, right? G transpose G. See, it's very all pretty much similar, right? Well, is equal to the estimates of S, because if you substitute G here, you will get identity, right? And you will isolate each element of S. If you're optimizing all together, then your inverse will be aware of the presence of the second and of the third sources. And if you are just looking as your W filter, it will be just simply G1 transpose divided by G1, G1 transpose G1, right? Without being aware of this guy and of this guy. Then, of course, it may not necessarily be orthogonal to this guy, the filter, or to this guy. It will not be most likely, okay? And you will have leakage of this source and of this source into your estimate. But if you optimize them all together, then you will exclude this. You will exclude the leakage into the into the estimate of the first source from the two other sources, because you know where the sources are, okay? And you have this luxury of specifying, basically saying that I don't want these guys to leak into my estimate. In beamformer, you don't know where they are, but if you are beamforming to a particular location, you say that, well, I have three potential sources there, and they may be, the dipole can be rotating, therefore each source may be active slightly differently, or maybe not even slightly differently, but differently, and therefore I want to estimate first X, then Y, then Z, and I don't want estimate of Y leak into estimate of X and Z leak, and therefore I'm optimizing them all together. See, you get exactly the same story, except that it's just scaled with, it's just scaled with R, but this isn't it exactly the same? G transpose G minus first G transpose G minus first G. It's the same thing, it's just scaled with R. It's just the same thing, but in this different space, whitened with respect to R. It's all the same. See, that's the problem, It's on the one hand, it's a different approach, but you can interpret it based on the very simple, basic setting. Okay?
Okay.
Yeah. All right. So that was the beamformer. The first beamformer was when we said in the first beamformer we said that we have a brain, we have a source, dipole G1, and we want to listen to it, right? And then I tell you that you have to choose W, which is R minus 1 G1, G transpose R minus 1 G, okay? And then you simply multiply it by your W multiplied by your X of T, and you get the estimate of the time series, right? Then the second beamformer was, you have this location, but you have three dipoles here, and you wanted to we wanted to make we wanted to make a filter that listens separately to the three orientations of dipoles, to the dipoles oriented to 3D, but in the same location. So so that you say that your W, which is now a matrix, which is a set of filters, right, is equal to, let me see, I always, this is something I always forget, is equal to R minus 1 G multiplied by G R minus 1 G minus first, right? This is matrix, this is matrix, this is matrix, this is matrix. And in this case, G is simply GX, GY, GZ topographies of these three dipoles, right? So it's GZ, GX, let's say G, whatever, GY, whatever, the other way around, but anyway, it doesn't matter. So, okay. So, and then your W, and you simply multiply your W by X of T, and you get S first source X of T, S first source Y of T, S first source Z of T, okay? And then theoretically, you can even from this, because these are just coefficients of your dipoles. Of course, it's active with amplifiers and so on. But if you want to compute the orientation of your dipole, you simply can take these and normalize it. You, at each time moment, you can normalize these by the sum of squares, and those will be your cosines with each of the directions, and will tell you about the orientation of the dipole. And you can see how changing, for instance, periodically, and for instance, and if you believe in cortical traveling waves, which I do, then you can basically you can say that you are tracking how a dipole is moving from this location to this location to this location, and then again, like, okay, it's rotating, but in fact it's moving from here to here on the cortical surface. Okay. But because the dendrites are oriented orthogonally, we will see it as a rotating dipole. But of course, it's not rotating; it's moving along the cortical mantle. Okay. So, all right, that was the beamformer to listen to a location. But also beamformers are used to estimate the sources, where they are actually, to find the location where they are. But the way they do it, the way the beamformers are applied here, is we simply scan through the entire brain. We make a beamformer to each location. One location, another location, second location, whatever, all. And then we simply compute the power at the output of the beamformer. And that's our answer to, to the problem, right? So, and the scan, the beamformer scan actually becomes increasingly, like, it's so simple that you can't even imagine how simple it is. I will show you. So let's first just simply formulate it. Okay, so you have a brain. If you have a grid, the brain, you have a set of locations. And let's, for simplicity, because I just want to conceptually introduce this, right? You have, at each location, you have topography G sub I. And for this location, you want to make a beamformer, which is W G sub I equal 1. And for this beamformer, you want to minimize the power WI, right? WI, you want to minimize this, right? When you make, then you do this, then okay, you found this, right? You found this. What is this? It's R minus 1 GI divided by GI R minus 1 GI. Agreed? Right? So, and then you go to, again, then you say I equal 1 to n, where n is number of locations, and then you can simply this is a vector, right? This is a then you can simply since you apply your data W times transpose times you made the data, then you form a matrix W, where each row of this matrix is simply the filter, right? The spatial filter that you find with beamformer, simply beamformer, etc. WN transpose, and it's a matrix. its number of rows is equal to number of sources, right? Well, I mean, number of dots here. And number of columns is equal to number of sensors, right? Because your W, you have to multiply it by your data, right? Your data multiple time series multiplied. So you take each row, each element here by x1, by x2, by x3, etc. Okay, and this is your scanning beamformer inverse operator. Okay, and then you can at every moment in time you can estimate vector of activities of all sources. S of t is a vector as W times x of t. Okay, that's it. But there is one little thing. Of course, you can do this way, but typically when we talk about beamformers, we are interested in estimating the power of source. Of course, you can take the time series of this, but if you take the time series, they can be slightly, one is high, the other is lower. Very difficult to say about the distribution of sources. It all will be breathing all the time, and not necessarily that breathing will reflect the real breathing, but maybe just artifact and stuff. So usually it measures the power, right? So, and we were minimizing the output power, right? And of the beamformer, such that we wanted that the only thing that is left after this optimization process is the power of the ice source, right? And therefore you can measure this power, right? How? Let's say for the ice source, it is W I transpose times x of t, right? What is the power of this guy? Si of t is equal. I exclude dividing, right? But it's just simply wt x transpose w. Agreed? And if you take because if it's a matrix, right? It's a matrix. It is basically wi r wi, right? Clearly, right? So the power of the I source is this. Now let's see here. You know that wi is r minus 1 g sub I divided by g sub I transpose r minus 1 g sub I, right? Well, substitute this into here because that's w, right? Well, g I transpose r minus 1, right? R, right? And then what? R minus 1 gi, agreed? In the numerator, divided by g transpose r minus 1 gi to the square, agreed? Well, this minus 1 and this r, they annihilate, and then you have gi transpose r minus 1 gi divided by gi transpose r minus 1 gi. This is a scalar, right? Scalar, square, is equal to 1 over gi transpose r minus 1 gi. That's the power of your source at the output, okay? So this is the square of the power. So basically, you don't even need to compute these W's. All you need is to compute the covariance matrix of your data, take the forward model, and do the scan. And that will be your your beamformer scan, the distribution of power of beamformer. Okay. So now let's look at this analysis a little bit, so that you feel a little bit less. So let me. W is this, so we substituted this into here, but let me ready. So this guy, right, is here, right? And then we continue here, and then we arrive at here. Okay. So see, it is as simple as this. So power of the power of the I source, the square of the power, is equal to G estimated with beamformer R minus 1 GI. You may say that, well, this may be bullshit because, come on, we have the numerator, everything is in denominator. I tell you yes, but well, it's not bullshit. Well, I say you yes, it may look suspicious, but if you notice here, it's inverse of covariance. It's inverse of covariance. It's multiplied by GI on both sides, right? And basically you compute the norm of GI with respect to the inverse of the covariance, but it's inverse of your data. And you divide you 1 over this. So in fact, it's again the square of the units are square of your data, right? Of your so it's not my 1 over square, but it's a square, right? Because it's minus first. If you had those like voltages, right? Then will be a covariance matrix of voltage squared, right? Then GI, which is, as we agreed already, right? It's a resistance, right? In the EG, for instance. Then resistance multiplied by voltage by resistance will be current. But because it's minus 1, so it will be 1 over current, 1 over amperes, but then because 1 over amperes will be amperes again. So it's the same units, okay? So this is okay, right? Now look how to interpret this also. Remember this whitening, space whitening, right? Assume that R minus 1 is R minus 1 over 2. Not assume, but represented as R minus 2, right? And assume that you're in a different space, right? In your whitened space, right? Then in this whitened space, all you are looking at is you are looking at the at this you are looking basically at the norm of your GI with respect to this matrix that transforms the space to make it spatially wide, right? To make the data in the space spatially wide, right? And depending on how much you need to transform it, you can make a judgment about the presence of this or that source. Okay, that's essentially what this beamformer power distribution is. Okay, and then yes, you do this very simply because remember when we were doing in MATLAB script, we were doing the scanning, right? We were doing the scanning, and we had dipoles, and we took the GI, and then we took our like data, we took our covariance matrix of the data, or even extract a single subspace, we measure in subspace correlations. Well, that was one story. Another story is to do this scan. It's very simple, very simple, very trivial. Okay, and let me erase this. Yeah. So, and this is a matrix, right? So, and that in this way you create you create a scanning beamformer. Okay. Now, in the data, there is one problem. There are many problems with this approach. Okay, but it works. It's still one of the best approaches. It still works the best with real data. It's amazing, but it is. So there are problems. The first problem is that the first problem is this. If you consider two sources, right? One source located somewhere in the surface, and some source located somewhere deeper in the brain, okay, somewhere here, right? So that the distance to the sensors is different, right? It's close to this and to these guys, and far away with these guys, right? And clearly, this difference will be present in GI, right? Say, for instance, if I want to say what signal will I measure at x of t if my source is deep, let's say deep times s of t, and they have the same activation, they have the same power of activation. It's the superficial one and the deep one, okay? Then clearly my measurements should be weaker for the deep source, right? Just because it's deeper located, it's further away, right? Therefore, the norm of G deep will be less than the norm of G superficial, right? because the G superficial this is a forward model. It tells you the amplitude you will see on the sensors due to a source with unit amplitude located at this superficial or deep location. Okay, and therefore, if you assume that you substituted here, you clearly will see the bias, even if your covariance matrix is exactly the same, right? And you will automatically be assigning greater power to the to the superficial source than you will be assigning to the deep one. Okay, and this creates a bias. This is what's called, we have a paper on this, but like in 2005, which is called a what you call whatever, I forgot how it's called, but basically it tells about, analyzes this biasedness of this beamformer and stuff, right? But what you can do very similar, very simple thing. Well, usually we record, there is such thing called neural activity index. Typically our evoked responses look like this, right? We always have pre-steam interval and we have post-steam interval, right? And this is the moment when the stimulus arrives, right? We usually average our evoked responses with respect to this location. Okay, neural activity index is interested into how much of power in the source space, or even sensor not the source space, was added after the stimulus, after the task has commenced, right? So and for this you can do this, what you can, for each source, source, you can say that, I know, well, the power of this source based on the post-steam data is this, right? And based on the pre-steam data for these very sources, right? This is post. And this is for this very source, this is pre, is equal 1 over gi r minus 1 pre gi. Okay, to transpose, of course, right? Vector matrix, vector, right? And then you say, well, and then I'm interested in power in this time moment. I mean, in this time interval, for instance, because R is computed, you assume that R is computed over the interval of the post-steam. This is R post. And R pre is computed over the interval of the pre-steam, right? And then basically you say that neural activity index is equal source power post squared, right? Divided by SI pre squared, right? And that's clearly GI transpose R minus 1 pre, right? GI divided by GI R minus 1 post GI. And that's your neural activity index as estimated with beamformer. Very simple, isn't it? All you do, take your data, take your evoked responses, estimate covariance pre and post, take your forward model, G sub I, and for I equal from 1 to N, NAI sub I is equal GI prime R, whatever, inv, right? Better inverse before, inverse pre multiplied by GI1 divided by G1 prime inv R post GI. That's it. Okay. Make it read better a little bit. Inv R pre. Okay. Multiply. And this guy. Yeah. Okay. And that's your neural activity index. That's all. This is a beam. This is something that you get with beamformer, and it's amazing that beamformer indeed works best out of many methods that we've played with. Well, dipoles work okay, but for some specific applications when you really know that you have one or two sources. Okay, beamformers Well, allow for more sources, can resolve more sources, and because they focus only on those sources that are active, right? They have this property of spatial super resolution. Okay, we have a paper on improving the beamformers because they fail in the environment with correlated sources. Okay, so basically, mm, in the situation when you have you have like you are measuring auditory response, right? For instance, you are measuring auditory response with and you are playing the sound in here, and you're playing the sound in here. Even in the one ear, you got synchronous activation in the cortex here and in the cortex here, right? And because of the synchrony, when you are beamforming for location in this guy, the beamformer will use synchronous power of sources in this other location to cancel, to minimize the output, and therefore will screw up the entire distribution. This is actually very similar to how the jammer works. Okay, if you take radar, which is like if it's in a military condition and you are listening to some aircrafts or whatever, if you know at which frequency our radar is working, you can generate a jammer so that the jammer signal will be taken as a tool to minimize the output power and yet maintain the constraint. You will still be listening to this, but you want to keep power minimized. Here is the source. Here is something that is very synchronous to the target source. So I will use this to minimize it, and then your power will be misleading. Okay, your power distribution that you will obtain will be misleading. We'll speak about it later on the next lecture very briefly, and then we'll switch to the minimum norm estimates, to the working course of inverse model and an EEG. But beamformers in MEG, but beamformers are very actively used now in many applications in spike, in intellectual spike analysis, in connectivity analysis, where they tend to try to use to estimate the time series of each source, and then you compute all possible synchrony measures between the sources. But the mathematics behind them is this, and for beamformers to work properly, covariance matrix estimate is the pivotal thing, right? As you understand, right? Because nothing else they depend upon. And the accuracy of the forward model. The forward model has to be accurate enough. So for the magnetoencephalography, beamformers work pretty well. For EEG, but the forward model is less accurate, they more complicated to make and work properly. Okay, but you can always do some tricks. You can regularize your covariance matrix a little bit, make it, you can do a trade-off between the spatial resolution and the fact that it will not cancel the signal. I will explain you when this cancellation is coming next lecture, and and we will switch to the minimum norm estimates, which is a global method. And see once again, in the beamformers, when we formulate the beamformer, I never told you about minimizing the difference between synthetic data, something, and the real data, right? It was nowhere when I told you that listen, we have this distribution of sources, and then we will, let me see, and then where was it? It was here. Yeah, and then we will have the distribution of sources, and then we will, hold on, was somewhere. I remember it was also green. Yeah, there. So we have something, our data, our real data is black, red one is what we reconstruct from our sources, how they, and then this is the error that we want to minimize. No, we were all like just all beamformers are formulated by listening, by setting the task of listening to a particular direction, and that's it. And you don't care about the global picture. Of course, this global distribution of sources and powers that you will obtain with this, not global, I mean on the whole head estimate or neural activity index, or just the numerator of this, denominator of this, they will not, you can't say that, okay, these are my sources, I will activate them with these intensities and I will get my data. No, you can't talk about this. It's just an estimate of the distribution of power of your sources. Okay. And if you do this like neural activity index, if you divide post-stim by pre-stim, then you get an unbiased estimate of power distribution, which is a pretty cool thing. Okay.
Can I ask questions?
Yes.
So before this neural activity index, we were talking about how with beamformers we can locate the source.
Yeah, yes.
Oh yeah, we again solving optimization problem. Well, first question is how we are choosing the location, the direction of beamformer. And the second question is, okay, we're solving optimization problem, we're obtaining this minimizing arguments, and then we're plugging them, obtaining the power of the source, power of the sources. And then you said that from distribution of power of sources, we can somehow infer the location. Am I right?
Yeah, yeah. Well, of course, yeah. Yes, you're right.
But
See,
but I don't
you
know.
well, okay, you say that it's circular argument. No, you are scanning. You are scanning like here. Sorry, I remember this European on my shoes. Sorry. Anyway, so here you are scanning here. Your beamformer is scanning in all directions.
Mhm.
Here, remember this radar, how it looks like. Your radar is rotating, and you see these planes, whatever. So the same story here. You choose GI, every GI on your for every eye in your cortex. You have a cortex model. You have a mesh, right? It's a mesh, right? You
Yeah.
have nodes of this mesh, and for every node you are placing a dipole. You basically, and you say that, okay, this is a dipole. You can fix its orientation, for instance, or may you don't have to, but I mean you may. And then this is the topography of this dipole, and let's beamform at this location and measure the power in this location. Then let's choose another location and do the same thing. Then let's choose yet another location and do the same thing, and etc. And do it for every location. Scan. There your locations are angles. Here your rotation locations are simply nodes in this grid. Okay.
Mhm.
In a radar, in a classical radar, it's just rotating thing, right? So you're rotating your angle and you're listening to different like targets, right? Here you're scanning through the entire brain surface and measuring the power. And the premise is, if the power in certain location is greater than in the other location, or in other locations, then this is where your sources are. But then I mentioned that it may be biased. It is a biased estimate, and therefore, to make it unbiased because of the dependence on on R on the depth, right? But on not G on the norm of G on the depth. But then to make it unbiased, let's measure not the power, but the amount by which the power increased in the post-stimulus interval as compared to the pre-stimulus interval.
Okay.
And that's what neural activity index is. But again, I here see I is brain location, and those are all locations. Like, well, I is like from 1 to 10,000, for instance. But it's very fast. It's very fast to compute.
Yeah,
I
okay.
still have a question, if
Yeah,
you don't mind.
yeah.
As a recap, because I might have misunderstood something on the way, beamforming is a technique that was taken from some other field, like radars and stuff.
From
right?
radar theory. Yes, yes, yes.
Yeah. So in that field, it's quite important to know the distance to the object. So original beamforming kind of have to allow for defining the distance.
Yeah,
In
the way
our case, the depth.
Yeah, well, the way not quite. See, in classical beamforming, the distance they're measuring the distance this way. They usually these radars, they are active. Okay, so they're sending a pulse, radio pulse. Okay, they're sending radio pulse
Okay.
at beam. The beamformer. The thing is, but the beauty here is that you have to apply the same coefficients to your emitters to send the pulse in a certain direction as you have to use when you want to listen to a pulse from the same very direction. Okay, so basically you have these coefficients, you send this pulse out, and you stay at this location and you wait for the pulse to come back. Okay, you wait for the pulse to come back, and then you are estimating the time difference between the moment when you send the pulse and when you received it, and that's how you measure the distance.
Okay, is that kind of the same principle that works in that stimulation technique you were talking?
Well, when did I talk about stimulation?
Um, the neural something power.
NAY, this thing?
Yes.
No. This is very different. No. This is neural
So
activity. This is a neural activity. This is simply imagine you do beamforming, you measure this power in the post stimulus. You have some cognitive experiment. Okay, you present pictures, for instance, right? Or you make some sounds, you play some sound. You notice the moment, you compute the evoked responses, okay? Like classical evoked response, right? You have pre-stimulus interval where you assume nothing is happening, and you have post-stimulus interval where the interesting stuff is happening, right? Then you say that, okay, let me beamform and estimate the power in the post-stimulus interval and compare this power to the what I had in the pre-stim interval, in the pre-stimulus interval.
Okay, so the latencies in post-stimulus interval do not matter. The latencies.
Well, you select the latencies, but it's not about the latencies that you measure the distance, whatever. No. You just still you have the you have that's the time series, right? That's your
Okay.
channel data,
Okay.
right? This is your pre-stim, this is your post-stim, right? You just take the post-stim, compute the covariance matrix on the post-stim, take your pre-stim, compute the covariance on the pre-stim. It's the time here is because you know that there was no task before this and there is task here. Or if you have a spike, for instance, right? You have spike like interictal spike, right? For instance, right? You can compute the covariance. It's not that great, but still you can compute the covariance on the interval of the spike and on the pre-spike interval, by the way, the slowing that we spoke about, right, yesterday. So anyway, so you compute the spike before, and you can compute the images distribution of activity with beamformer during the spike and before the spike, and you can see where you have the increase. Okay.
Okay. Thank you.
Is it, Nastasia, is it okay? I mean, but I think that your question is deeper, but I just somehow didn't catch it.
Oh no, you have actually like I got the answer. I had another question, but the previous question and answer mostly got that because even though we don't have the direct measures from power to measure the depth of the source, it's just a very actual task in clinic because we are often asked how deep the source is. So it bothers me.
Yes.
Even though we don't have the direct measures to using beamformer based on the power.
No. Hold on. I tell you, Okay, see, no. In fact, we have an option to measure the depth. Okay, but we don't speak about it as a depth. Okay, but we just speak about as a location somewhere. Okay, because see, if we have because we can distinguish sources if they have different topographies. Okay. If they have different topographies, we can set the problem and we can separate. We say that, okay, this guy's with this topography, this and with that topography, right? If you had a source, if let's say you have two sources, okay, the first source is this, has topography like this, okay, this is positive, this is negative, right? And let's say you have another source, whatever, where it is, yeah, you have another source that is this way, and then I want black, okay, yeah, go black, so, and I have this. So see, in fact, each point here, there's sensors, right? There's points are sensors here. So you have different topographies. So this has G superficial, in fact, right? Because it's and this one is G deep, right? Because it's more spread out, right? It corresponds to a deeper source, right? And therefore, when you're doing beamforming, you will be able, especially if you compare pre-stim and post-stim, right? Or pre-spike and post-spike, right? During the spike and pre-spike, you will be able to judge about the depth just because you will be able to say where they are. Because depths will be encoded in the location. Okay, this is one story. Another story is if you talk about the depth of the source, this is like very advanced on the cortical mantle. Okay, so it's a cortex, and you are interested in which layer of the cortex your source is. And that is complicated, okay, because it's very thin. It's like about what, 3 millimeters, 4 millimeters, and the topography difference, of course, is not very big, of course. But what you can do, you can measure, you can have statistics like Friston, not Friston, this guy, Garrett Barnes had a paper on this, but it didn't work really, but he tried, okay? So he was modeling having physiological knowledge which activity from which layer goes to the dendrites, to the dendrites of pyramidal neurons, to drive them. And he was trying to model this in order to recover in which layer of the cortex the source was. But that's a completely different story, okay? But with this depth, no, we have a tool to estimate the depth, but this depth is basically encoded in location, okay? Because if you have a like brain, right, then whatever, I don't know, I can draw it. Well, it was, I'm afraid to draw something. Well, I already drew something horrible. Yeah, anyway, so if you have a brain, if it's deeper, then simply have different location, and that's what you will be able to recover. But of course, to a certain extent, because some resolution, and the depth resolution is not that great, you're right. Whereas the resolution with respect to rotation of the source is very good in the EEG and image. Yeah. Okay.
Okay. By the way, I came to the library and I have Ivan here with me.
Ah, say hi to Ivan. Ivan. Anyway, he's shy, but he never was shy. But anyway, yeah, all right. So it's time already. It's 19:30 here. And I wish you. Did you complete your homework, by the way, or you still have time to complete it?
We still have time.
Ah, okay. So yes. So do complete it, and then we will have another homework for you. Will be more practical to play with some data. So Dasha can help you a little bit with this. And so again, the goal of the class is to not so much, of course, like make you developers of methods. Of course, this is impossible after like 6 lectures or 7 lectures. But at least somehow understand, or at least attempt to understand the mechanics behind all these beautiful Python scripts and stuff, okay? So that you at least more or less a little bit understand the constraints, the limitations, and what is actually going on, okay? There is and yes, I'm trying to give you details, mathematical details. There is this guy named Cohen, David or whatever was his name. Yeah, he has this beautiful book, and the book is completely opposite to these lectures. Okay, it tells about if it was to tell you if it was to tell you what I told you with these details, it would probably took him about 700 or 800 pages. Okay, so therefore, if you
Mike Cohen.
Mike, sorry, not David. Mike, of course, David is a different guy. There's also Cohen, but the MEG guy. Yeah, Mike Cohen. Yeah, and this is his book is beautiful for most likely for the people who want to relatively superficially, but iteratively many times go over pretty simple stuff without very going deep into math details. I'm on the contrary, I'm trying to somehow show you the math details and show on the one hand attempt to show how in fact beautiful it is because it's despite my handwriting because it's all very much interrelated, and you can build intuition. And the reason I'm doing is because based on this intuition that I have, that I built for myself during my years of like studying and teaching, and since I'm able to develop new methods, okay, because I'm not developing them based on on the strict mathematical, manipulations. I just feel somewhere in my head that this has to be this way, and I then put it in writing and derive the formulas and prove it. Okay, so and that's all based on the intuition. That's why I'm trying. Of course, I understand that this is not very simple, and especially since our things which are like have a lot of symbols may be misleading, but I'm trying to like make connections to some real life examples, like listening to a crowd or to a person in a crowd and things like that, for you to build some understanding. Okay.